Hello student. Today's topic principal component analysis. Principal component analysis, its PCA, is a statistic procedure that uses an orthogonal transformation to convert a set of a observation of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components, or sometimes principal modes of variation. The number of principal components is less than or equal to the smaller of number of original variables or the number of observation. This transformation is defined in such a way that the first principal component has the largest possible variance, that is, account for as much of the variability in the data as possible, and each succeeding component in turn has the highest variance possible under the constraint that is orthogonal to the preceding components. The resulting vector are an uncorrelated orthogonal basis set. PCA is sensitive to the relative scaling of the original variables. Now, PCA is mathematically defined as an orthogonal linear transformation that transforms the data to a new coordinate system such that the greatest variance by some projection of data comes to lie on the first coordinate, called the first principal component, the second greatest variance on the second coordinate, and so on. Mathematically, the transformation is defined by a set of p-dimensional vector with weights or loading wk that equals to omega 1 dot pk that map each row vector xi of capital X to a new vector of principal component scores ti that equals to t1 tm I given by tki that equals to xi wk for I equals to 1 to n and k equals to 1 to m. In such a way, the individual variables of t considered over the data state successively inherit the maximum possible variance from x, with each loading vector w constrained to be a unit vector. Now we are discussing about first component. The first loading vector w1 thus has to satisfy w1 that equals to argmax w equal to 1 summation I t1 square I that equals to max summation I xi w square. Equivalently, writing these in matrix form gives w1 max equal to 1 square that equals to max equal to 1 wt xt and xw. Since w1 has been defined to be a unit vector, its equivalently also satisfies w1 that equals to max omega t xt xw divided by wtw. Next we are discussing about further components. Further components. further components. The kth component can be found by subtracting the first k minus 1 principal components from kx. Xk, that equals to x minus summation s equal to 1 to k minus 1 x ws, that equals to wts, and then finding the loading vector with extract the maximum variance from the new data matrix. Wk, that equals to max w equal to 1, w that equals to max transpose xk transpose w by that. It turns out that the gives the remaining eigenvector xtx with the maximum values for the quantity in brackets given by the corresponding eigenvalues. Thus, the loading vector are eigenvector of xtx. The full principal components decomposition of x can therefore given as capital T, that equals to xw, where w is a p by p matrix whose columns are the given eigenvectors of x transpose x. Properties and limitation of PCA. Now at first we discuss about properties. Here property number 1. For any integer q 1 less than q less than p, consider the orthogonal linear transformation y equal to b dash x, where y is a q element vector and b dash is a q cross q matrix, and let summation y equals to summation y, that equals to b dash summation b be the variance covariance matrix for y. Property number 2. Consider again the orthogonal transformation y equal to b dash x with small x, capital B, capital A and summation y defined as before. Then TR summation y is minimized by taking capital B equals to AQ star, where AQ star consists of the last q columns of A. Property number 3. Spectral decomposition of summation. Summation, that equals to lambda 1 alpha 1 dash plus dot 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 plus lambda p alpha p and alpha p dash. Before we look at its usage, we first look at the diagonal elements variance xj, that equals to summation k equal to 1 to p lambda k alpha kj square. Now we are discussing about the limitation of PCA. Limitation. Okay. The result of PCA depend on the scaling of the variables. The scale invariant form of PCA has been developed. The applicability of PCA is limited by certain assumption made in its derivation.